It was a consultant from not even in our school. They're from Logan. Whatever. That's the goal. All right. There's a bunch of words up here that I'm not going to choose to care about. It's kind of like the ACT. I'm going to care about the table. So you may recall the rate law. Rate was equal to K times the concentration of A raised to some number and B raised to some other number. All right? When we use initial rate data tables, what we're doing is we're changing the rate. All right? By doing that, we can solve for this unknown exponent. Okay? That's all we're doing. We're changing the concentration of 1, seeing how it affects the rate. And if the rate does the exact same thing that the change was, we said it's a 1. If we change it, though, and the rate is multiplied by another number, then we know our exponent must be something besides a 1. And it's usually a 2 or a 3. So here we go. You want to find two places where something is held constant. So it's just habit from when I was your age. I moved to A and B. So when A is held constant and B is changed, I can get data about B. Now, once in a while, you do it 100% back because you just switch what's being changed and what's constant. So right here, from here to here in trials 1 and 2, B, the concentration is double. You okay? I'm basically 2 timesing whatever it was before. All right, now I look at my rate, and if I take 208 and divide it by 52, I end up getting 4. So we said, all right, if I put a 2 in these brackets, but it generates a 4, then it must have been 2, and the exponent now must be a square. Okay? Because that's the only way changing something by 2 can actually change something else by 4, is if your change was square. Okay? So we would now say in this rate law that we know this number is a 2. Are you okay with how I just did that? All right, good. It's easier the second time, right? All right, now let me erase this. And now I look for when this one's held constant. So here it is constant, and as I go up, I multiplied it by 2. So I look up here. As I went up, I pretty much multiplied it by 2. I know it's a hair off, but we're not going to care much about like just a tiny bit. All right, so if I'm putting a 2 in here and holding that constant, and my rate is also 2, then that must mean this exponent is just a 1-to-1 ratio, which is the only exponent that does that, is a 1. You okay with that? If your concentration change equals your rate change, then your exponent's a 1. Okay? If the change is the same, your exponent's a 1. So now we know the official rate for this, or rate law would be rate equals K, which we'll solve for in a minute. And I'll go ahead and substitute the things in now. HgCl2 to the first, and C2O4 minus 2 to the second. Who's with me so far? Thank you, sir. Not here. All right. So now, according to the data shown, what is the rate law for the above reaction? We have this is not working with my hand. That's always fun. When it's like 3 seconds behind your movement, it's kind of hard. All right. So we have A. That's all set. B, on the basis of the rate law determined in part A, calculate the specific rate constant. Specify the units. Go ahead. Yeah. The rate law is the general statement. It's just that. If you already found k, like you can write it in, but you don't have to. All right. So to solve for k, we just use algebra. We take k equal to rate divided by these two things. You okay with me rewriting it that way? So k equals rate divided by hg, I don't know why I forgot the h, Cl2 to the first, C2O4 minus 2 to the second. All right. Now, that's the algebra to solve for k. Now we just got to plug everything in. So I can take any of these rows I want. It could be row 1, 2, or 3 because it has all that data, and just plug it in. I typically choose row 1 or the row that has the least number of numbers to type into my calculator. Whatever. Do whatever you feel like. So in row 1, the rate is equal to 0.52 times 10 to the negative 4. Okay. In experiment 1, my concentration of HgCl2 was 0.0836, and I raised that number to the first power. All right. So that was this one. In experiment 1, my chromate, no, sorry, that's oxalate, C2O4, why am I writing that again? Whatever, my oxalate concentration was 0.202. And what do I do to that number? I square it. I have selected the pen tool like 3 times, you piece of crap. Thank you. And I square it. And I plug that number in. Or those numbers in. Now, my regular chem students learn this lesson all the time. The entire denominator should be in parentheses. If it is not, what you do algebra-wise is you take this number and you divide by that number, and then you multiply that answer by 0.202 squared. But that's not what we want. We want these two under. So parenthesize the denominator. Anybody have an answer for me? 0.015? Okay. So that is our K value. And if you felt like writing it right here, you could. Rate equals 0.015 times that times that. Okay. Now is time to solve for the question mark. So the question mark is really this value right here, right? Okay. So I'm going to rewrite this whole thing. So rate equals 0.015, all right, times HgCl2 to the first times C2O4 minus 2 to the second. Correct? All right. Now, this is my x. Are you okay with that? So I'm solving for this. So algebra-wise, that means rate, and I can plug these numbers in, right? But I'm just going to write it out the long way. That x is equal to rate divided by 0.015 times HgCl2 to the first. Okay? And that equals my x. Well, yeah, that does equal x squared. Thank you. So really, x will equal... Why are you not working, you piece of junk? X equals the square root of all of this, correct? Okay. We just plug it in. The rate is this, 1.27 times 10 to the negative fourth. I'm going to beat this thing. It worked until the day. 1.27 times 10 to the negative fourth. HgCl2 is the given right there. 0.0316. And that's just to the first. And then we do that math, square root it. Anyone agree with that number? 0.33? All right, I have 2.5s. 0.5? Because x in this thing, x is really squared. So to solve for just x, I have to undo a square by square rooting. Okay, 0.5. All right. Okay, that is a super typical test question. It would be just like the one on your exam that you have to do for me. If there's one of these on the AP test, you have a 99% chance it's just like this. All right. So this would, C would have been like, what's the question mark? Okay, now, there is this piece right here that says specify the units. Let's get good at this before I complicate it with units. All right, so let's do another problem, and we'll see what we got. Okay, given the data rate for rate data for this, what's the rate constant? Or sorry, what's the rate law? Constant. Solve for x. We'll give you a few minutes. All right, so we'll go through all of it, but for B, I think I saw 6 point something was your answer. Is that right? 6.3. And this was 0.487 or something like that. 48 what? Okay, 0.48, we'll call it good enough. All right, if you do not have these two answers, then make sure you're 100% with me. If you do, you can kind of relax because you did it right. All right, so these are constant here. This is doubled, and this became, so this was a 2. If you square it. So NO will be raised to the second, correct? And then H2. In H2, this one's held constant. This one is, that's a C. This is times 2, and the rate is times 2. When the change is equal to the change in rate, your exponent is a 1. So now rate is equal to K times NO squared H2 to the first. Yeah, I always look at it that way. Look at if it's halved, then it must have been to the second. That gets confusing. You can. All right. So who at least had the rate law correct? Would you raise your hand? That's a fair amount of people. All right. So then you solve for K. K is equal to your rate divided by NO squared and H2 to the first. Well, that's ugly, but whatever. So I'm going to plug it in on this side. I'll go to the top, 0.136 over NO, which is squared, 0.420 squared, and 0.122 to the first. Sound good? And then hopefully when you plug it, make sure you put the denominator all in parentheses. And I erased it. Was that 6.3 or 2? I don't remember. 6.3. That's K. Then I'm now solving for X, which is in H2. Is that correct? Okay. Let's see if this will work. So X, I don't give this thing because buttons have switched on it over the weekend somehow. All right. So X, I'm going to leave it here and put my equal sign that way just to kind of keep everything clear. I have rate on the top still, and then these two things go on the bottom, correct? So 6.3 times, and I'm just going to go ahead and plug it in. NO2 was this value, 0.105 squared. Okay, I should have just written rate right here. Oh, geez. Now what's happening? 0.0339. Okay, when you plug all that in, oh my, geez Louise, Tom. Oh my gosh. Whatever. Not pleased, but all right, we feel okay with that. When you plug that in, let's see, I'll do it the old school way. Plug that in, you should have gotten 0.48. Is that what you guys told me? Okay. And fair enough. How many of you feel okay with this? Raise your hands, would you? That's the most hands we've had in months. Let's just celebrate for a second. Let's celebrate by doing another one. This one's easy. This is held constant, correct? What happened to your rate? All right, it was also times 2, correct? So we know X is just raised to the first. You okay with that? Okay, that's a Y right there, clearly, people. JK. All right, thank you. See, even I, perfect Tom Davidson, screw up once in a while. All right, Y. Thank you. Okay, now, the other one isn't that bad. Let's get rid of this. Okay, I'm going to shoot it so hard. I hate it. Why are you being so dumb today, you stupid pen? Thank you. Okay, now, let's just look here. This is doubled, right? And this is doubled, right? What happens to your rate? It doubled. Now go with me here. Well, it's a -4, so you are right, but it also is that. It doesn't mean it's the exact same experiment. It means, follow me here, that X is raised to the 0 power. Because if you look, just follow me here. We know Y doubles stuff. We know that because we learned it here, correct? But when we changed X, all we still got was a double, which we know Y accounts for. So if your change does not affect the rate, then your exponent is 0, because a 0 exponent turns this thing into what value every single time? A 1. You okay with that? I could have picked any row I wanted. It still would have told me, yeah, if I, so you wanted me to do which one? Here to here? That one's harder because you're not doubling it, you're adding it a half. So to me, that math would have been harder, but you can still do it. Any of them would have. Okay. Careful. Raised to the 0, you still need to write it in the rate law. Even though mathematically it doesn't matter. You would write rate equals K times Y to the first, X to the 0. You should include it, even though mathematically it's pointless, it is still part of the rate law. Okay, that looks more like an 8, but it is a 0. Okay, will you try part B? You can do that without me. So algebra-wise, we said that K was going to be equal to rate over y for this one, right? So this one was easy, and the units will be easy. So what you do is you go up to your expression and you find the units. Your rate are mole, liter, -1, second, -1. All right, I'm going to write just one line, and I'm going to take every part here. Mole is not to the negative, so I'm going to put it on the top. Liters is to the -1, so I'm going to put it on the bottom. Now, I'm only accounting for rate right now, okay? And then seconds to the -1 is also on the bottom. Are we okay with that so far? That is just the unit for rate. Okay? All I've done is plug it in. If it's to the negative, that means it's on the bottom of a fraction. Then I divide it by y. So y, if I have any negatives in y, they'll go on top, and any positive will go on the bottom. Now, you don't really ever have that, so don't stress. Y is just usually concentration. Okay, never mind. It's either molarity or moles per liter. Okay, so I guess I just lied. So mole, since it's on top, this is confused, or sorry, since it's not to a -1, then it's just here on the bottom. Now the reason why is because y is on the bottom. Since liter is to a -1, since it's in the denominator, it is reversed and it's on top. Are you ready now? We use algebra, and we say, okay, anything that's on the top and the bottom can be canceled out. So, yes, this was on the blue sheet. So 0.007 seconds to the -1, or 0.007 per second. Now, the rate constant is not always per second. It depends on your rate law. Let's go back to one we've already calculated. Okay, this one we said that K was equal to over NO squared and H2 to the first. All right, so my K units, I'm going to put just one giant fraction thing. I'll find the units for rate. All right, mole, liters, seconds. So it's almost always the same, by the way. Liters a -1, so it's on the bottom. Seconds -1, so it's on the bottom. All right, and then the next thing I had was NO squared, correct? All right, that's moles per liter, but it's squared. And since it's in the denominator, the units are inverted. So it would be mole squared on the bottom and liter squared on the top. So far we've taken care of rate, we've taken care of NO squared, and now H2 is going to be mole per liter, but it's on the bottom again, so it's inverse, so it's a mole per liter. Are you with me? Okay, then I cancel everything out. This mole is gone, these liters are gone, and nothing else cancels out, right? So the units for K, it's 6.3 liters squared per second mole squared. Now you won't ever see that written in a book. You'll see it as liter 2 S -1 mole -2 is how you would see that in a book. Both answers are fine on a test. See why I said they're kind of a pain? You have to be a very good accountant. You need to remember, if it's in the numerator, then the negative takes it to the denominator. If it's in the denominator, then the negative takes it to the numerator. Because math is cool like that. Okay. Let's try one more. So A, find me the rate constant, or rate law. B, constant. C, units. D, solve for X. I'm just making this up so it could be super jacked, but who cares? All right. So B held constant, A is changed, or sorry, doubled. What's your change here? That's a 4. Because this is essentially 25, and this is essentially 100. If you move the decimals like that. All right, so it's 4 times. So when A was doubled, we got a 4. So A, or NO, is squared. We okay with that? All right, when these are held constant here, oh, don't do it to me, and these are doubled, what was your change? It was 2x, so that would mean B, or just O2, was raised to the first. So my rate equals K times those things. How do we feel about that? Who had that part right? That's not as many as I'd hoped. All right, the constant, then you just plug and chug. So K is equal to rate over NO squared and O2 to the first. So let's plug that in. 2.5 times 10 to the negative fifth. NO squared. So NO in this one was 0.01. Squared and 0.01 here, correct? That's, oh my gosh, Tom, that's a 1. It did? It looked like sort of a 0, but oh well. And you're going to get something that's a 25. Okay. The units, it's going to be the exact same as the one we did in the example, the second example, if I remember right. I'm running out of time. But the units of K, all right, are, we had moles, sorry, so the rate here, mole, liter second, and then we had liters squared moles squared. You okay with that? For NO, that's the molarity squared, and then another mole and another liter. So the individual moles and mole and the liter and liter, so it's liter squared seconds mole squared on the bottom. Okay, then we're probably out of time. What do we get for X? Anybody? 0.0128 with a slashy above it. Did anyone have all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's pretty good. Okay. We'll probably start tomorrow off with just one of these. It's like a quiz. It's not going to count, but we'll check it. And then after that, we'll talk about the other way to do this, same thing. And that's the one that requires the calculator. It's not that bad.